Okay, welcome to class. We'll do the quiz in just a moment, but first we want to do a demo while there's still a chance that it might work. This thing's kind of time sensitive. So we have the MSc students cast a bunch of different metal alloys. And these are a special type of metal alloy that if you cast it, you can quench the high temperature structure down to room temperature. So I need 8 more volunteers that want to come try this. So come on down, 8 people. You're going to grab a metal object from this bucket of ice water. One of the stranger things you'll do today. If you're already an MSc student and did it, then you can't come down. So 6 more brave volunteers. Anybody? Nobody? I'm just going to start chucking them around the room. Come on up, Takara. Okay, grab one of these things out of here. What you're going to do is you're going to take it, you're going to squeeze it in your hand because it needs a little bit of warmth from your body to cause it to convert to the thermodynamically stable phase, right? There's a kinetic barrier. Right now it's in cold water, but when it turns warm, I'm going to guess maybe a third of these will get pretty warm. It should heat up on its own for maybe a third of them, and 2/3 probably won't work. So go ahead, as soon as you grab it, squeeze it in your hand, and then tell me if yours gets hot. So for example, it came out of ice water, you feel that, it's now quite warm. Look, I'm a magician, like convincing you that something's happening. So just pass that around. It'll probably stop getting warm momentarily. Okay, anybody else is getting warm? Or a bunch of duds, maybe? We have at least one work.
Well, it's not cold.
It's no longer cold, it's now hand form. Okay, while they are waiting for hopefully a few more of these things to get warm, let's try and explain what's going on. In this example, we made aluminum and zinc alloys, right? So we alloyed aluminum and zinc, we heated them up, we chose the composition to be exactly at 78 weight% zinc. The reason we chose that is because this is kind of a nasty looking phase diagram, and it's got some things that we haven't seen before, right? You've got this alpha plus liquid, alpha over here, but then when you start going left to right, you see something kind of funny. You see this point where alpha will split to alpha plus alpha prime, right? This region at the top of that little disk there, that is a 2-phase region, right? It's a 2-phase region because it's got one phase on either side of it, so it must be a 2-phase region. So what's happening there is that you have an alloy that's spontaneously decomposing into 2 different compositions, right? It's not happy to stay all together. And so this happens just like oil and water. If you take oil and water and you mix them, they'll spontaneously demix, right? They're immiscible. So that's an immiscible liquid. You can also have immiscible solids. Is that one getting warm? This one's getting warm too. Okay, so basically because of that, you get this interesting phase diagram. What we chose to do is we made it this composition, we melted it, we cast them into shapes. So by casting it, you pour it into cold sand in these kind of funny looking shapes, and now it's at room temperature. They then reheated it back up above this line. That's what's critical. It's got to be above 275. So now you're ideally in just this beta region. So that's just some crystal structure. If you leave it there and let it equilibrate, so all of it converts to the beta phase, and then you very quickly quench it into ice water and bring it down to room temperature, you don't give it time and the thermal energy that it needs for the beta phase to convert to alpha plus eta. But as soon as you grab this in your hand and you squeeze it, hopefully for some of these, it should be getting warm. It should be converting to the alpha plus eta phase. Either that or we didn't quench it right. Anything? That one's warm? So some of them? Okay. That's the idea behind it. And so if you wanted to do this accurately, if you wanted to measure how much heat was being generated, you would actually get it started in your hand and then you drop it in a little bomb calorimetry setup, right? You'd measure the water change in temperature and you know the heat capacity of water, so you can figure out how much energy it produced. And this is kind of how, well, it's at least the idea behind how some of these phase diagrams and the thermodynamic values are created. So thanks for participating, guys. You can throw those back in the bucket unless you want them. Okay, so let's start our clicker quiz for today. It's all yours. All yours. Okay, the first clicker question is as follows. When a crack splits through the grains... Oh, wait, this is yesterday's. Hold that thought. This is definitely yesterday's. We're not saving that one. We're definitely doing section 9.3 today. Okay, try that again. All right. First clicker question is, fatigue is A, common in load-bearing components, B, the lowering of strength in material due to repetitive stress, C, crack formation and crack propagation that eventually leads to a crack which is large enough to satisfy the critical flaw size for failure, or D, all of the above. Absolutely.
The rocket ship.
Okay, get your answers in. We're going to close the poll for the first question. Okay, people think A, B, C, or D. D is definitely the right answer there. Okay, next one. A material with a fatigue limit will continually grow weaker and weaker as cycles progress. True or false? Jeff. I mean, when you start from cycle 1, and if you cycle it to an arbitrary number, it will always grow weaker and weaker. Is that statement true or false? And by weaker and weaker, what I'm saying is it's going to fail at a lower and lower stress. Is that a true or false statement? Get your answers in. That is definitely false. When a material has a fatigue limit, basically it has a threshold, and below that it's not going to fail due to fatigue. So it doesn't get weaker and weaker. It gets weaker until a point, and then it plateaus, and then you're good. So aluminum doesn't have a fatigue limit, which is why aluminum will just get weaker and weaker if you flex it back and forth, but steel does. It reaches a bottom limit. In the fatigue fracture surface of a steel shaft that's shown here, below, which of the three regions illustrates the propagation of the fatigue crack with beach markings? So where do you see beach markings? Hint, they look kind of like a beach. Okay, we're going to close the poll. People think, hopefully B, yes they do. And then the last one, because I told the students that I'd have the class vote on this, they realized how hard it was to actually make shapes when you cast, I don't know, 700 degrees Celsius metal into sand. So you can choose your favorite of the things that were cast, and they're all worth a point. So Just vote your conscience. What's the coolest thing? And I will say, the fact that this one says Sparks is pretty freaking cool. This also says MSC, and that's cool. That's true. Letter D was actually a dragon that they tried to cast. There's no way I'm going to hear that question. Okay, so get your votes in. Doesn't matter what you pick, it's all worth a point. What do we think? People think E, which was the letter U. Good, fair enough. That's a pretty good. Okay, we're now going to pick up where we left off with last class, which is with this crack growth equation. So let me just remind you the question. It said the following. It said, a steel plate is given, and you know the fracture toughness. We're told that it's alternately loaded between 500 megapascals tension and 60 megapascals under compression. We know what the crack growth constants are, A and N, sometimes called C and M. Again, I apologize. I did not make the rules. Some people use different names for those. Yeah.
In the homework, we have A and M.
So M and N you can use interchangeably. It's still the exponent, so I apologize for that. Yeah. And then it asks, okay, if this thing has to survive 10 years being cycled every 5 minutes, how big can the largest surface flaw be? Because you're gonna assume that surface flaw is going to grow over the lifetime of this component. So how big can it be? So we set this up by first solving for the number of cycles that it had to survive by going from years to minutes, then dividing by 5. We then said, okay, the number of cycles will be equal to this 1 over A pi change in stress. This is raised to the n. This is raised to the n over 2. Again, the change in stress, we did not account for compressive stress, right? Because in this class, we're going to make the assumption that cracks only grow under tension, which is not always true. But for mode 1 cracking, that's the assumption we're making, right? That's multiplied by the integral from the initial crack size to the final crack size, or in other words, the critical crack size, dA y to the n, a to the n over 2, right? And then we reminded ourselves, how are we going to solve this question since it's asking for A naught, and we have 2 unknowns right now, both AC and A naught. We remembered that we can use Griffith fracture toughness equation to solve for AC, right? The critical flaw size is going to be 6.49 millimeters. So our initial flaw size, we know it has to at least be smaller than that, but how much smaller? So the next step, and for the next clicker question, I'm going to have you finish this question by evaluating what's in front of this integral, evaluating the definite integral, right? The defined integral, I should say, and solving for AC. So we'll do 5 minutes tops for this. And you'll put your answer in micrometers. Yes. Yes, in this case, you're going to assume that y is constant. If I don't tell you otherwise, you can assume that y equals 1.12, and therefore it can come out of the integral. And on a midterm, that's all I will ever do. On a homework, you have an example where you have to leave y in. For this class, you can bring it out on the midterms. And if you need help, we have a couple TAs, so by all means, raise your hand and we can come around and help. For those that have forgotten how to take that integral, I just write this, what the integral is. So 1.05 times 10 to the 6th cycles equals, well, let's just write a number, some number in front of the integral. And the integral, when you evaluate it, you're going to evaluate from AC to A naught, and the integral itself is going to be -5 over 3a to the 3/5. Right? Or in other words, which is the same as -1.667 over a to the 0.6. You evaluate that from AC, which you know, to A naught. Okay, another couple minutes, we'll wrap this up. I'm going to get this out of the way, but remember, you need your answer in micrometers. No, it's 0.
There it is.
Isn't it? Since it's 1.6 and not 0.6, then that'll be 3 bits.
Making sense? Oh, and just to clarify, to get this thing for the integral, that's assuming that you took y out of the integral, right? If you left y in, you'll get a different number here. I took it out. Okay, there was a good question on units. Somebody asked like, oh, do you have to convert this 500 megapascals to pascals? No, you can leave that in megapascals in this question. The way you know that is they normally give that in your units here for your A and M. In this case, if you leave that in megapascals and you do these, you're going to get your answer in meters for your crack length. So to go from meters to micrometers, multiply it by 1,000,000. Micrometers, micrometers, I don't know how you say that. Okay, for the sake of time, we're going to wrap this up in just a minute, maybe one more minute to get your answers in. If you're feeling desperate, phone a friend. If you're having clicker questions, you can, like, if your clicker's not working, you can always show me and I'll make sure you get your points. They have issues with decimal places sometimes. The decimal's not an option, or it doesn't work. My point is not to, I just want you to participate in class, so don't worry about the clicker points. I'll make sure you get your credit. Okay, we're going to wrap up this one. Okay, answers in, everybody. Wait just a second longer. Okay, I'm going to close it. Okay, so people think these are all right answers. 1.5 is a little bit out there, and then others are ones that were wrong. So maybe half right and half wrong. So let's go over this. Okay. If I leave y in the integral, I get 1.159 over a to the 0.6. Right, that's leaving y in, or you could factor y out and have the answer I showed you before. You're evaluating that from a naught, which we do not know, up to ac, which we do know, 0.00649 meters, right? I plug in the next step and I get is equal to 264.66 over a naught to the 0.6 minus 5438. And finally, solving for a naught, I come up with 9.97 times 10 to the negative 7 meters. And when you convert that to micrometers, you multiply it by 1 million. So that's just equal to 0.997 micrometers. So if you put in anything from like 0.8 to 1.2, you would have gotten the right answer there. Okay? If this is not clear to you, how you take that integral, in the reading that I've posted, they actually post a generic solution to this, right? They write it in terms of n, so you can punch it into that. So again, if you haven't done the reading on crack growth, it actually shows the math behind it. Take a look at that. It's under Files, under Additional Reading, and it gives you a generic solution. So if you don't want to be hassled with the integral, then just punch that in right on your note sheet and use that on the test. Okay? Any questions I can answer on this? Okay, we're going to keep moving then.
I have one question.
Yeah.
How likely is it that something like that will be on the test, and how much of that whole process will we have to know?
This will, without a doubt, be on the test, right? And you'll need to know how to use the NF equals the big long equation integral. You'll need to know either how to take the integral yourself or know how to use the pre-written solution that's in the book. You'll need to know how to use Griffith's fracture law, maybe to figure out a critical flaw size, assuming that you knew the starting flaw size, right? There's lots of ways to ask these questions, right? I could ask for the number of cycles till failure. I could ask for what the initial flaw size was, like in this one, or I could say how many cycles, if it lasts a million, how big was the largest flaw size when it did fail? So lots of things we could ask. I could have you solve for the critical flaw size, and then I could say, therefore, tell me what the fracture toughness of your material is, where then you plug that back into Griffith's fracture toughness. So a gazillion ways to ask questions about this. Just like before, we'll post a practice midterm that will show you a few ways we've done it in the past. But really, there's no substitute for practicing this and making sure that you can work it relatively quickly, because you won't have 15 minutes to work on just that part. You'll have about 7 or 8. Yeah, Jan?
Question about the first reading quiz question.
Question about, sorry, what's that?
Just the first reading quiz.
Okay, what was it?
So something under like a constant level, does that experience any sort of cyclical cycles of stress, or is it just purely?
Good question. If it's a constant load, we mentioned this last class, things can fail under a constant load. We call that static fatigue. It's particularly important for ceramics, right? Static fatigue meaning it's under a static, so it's not changing load. Well, first off, things are never totally static. There's always temperature fluctuations. There's always some oscillation. But also, if there's a little bit of liquid at the tip of that crack, it can undergo stress corrosion cracking, and the crack can grow because the liquid dissolves the ceramic material at the tip of that crack. Again, normally you might not think that your dinner plate is soluble, but at the tip of a very high curvature, meaning very small radius of curvature crack, there's significant solubility which incrementally advances that crack length. Yeah, Anthony.
So would it be not advisable to try to solve some variables first before you punch in the numbers? Because I kind of tried to do that and I just kept getting huge numbers, like e to the huge number stuff like that. So, and I don't know, I just throw it out on my calculations. Would we best just like
I've done
plug
that.
everything in and then figure it out later? Or?
I haven't typically had a problem when I do that. So I don't know what to say. Let's do some more example problems, and you'll see we'll work through a few more of these. Again, just like the other problems in this class, I've done YouTube examples of this, so you can see it worked out again and see the sort of steps that I took.
Okay.
Yeah. Other questions I can answer about this before we move on? I understand this is challenging, but honestly, it's one of the cooler things that you've learned, right? You've just learned an equation that tells you how many cycles till something fails. You know what's the critical thing that's going to make it fail. You know how to predict this. So based off of just the spec sheet that you get from an employer, all of a sudden you have quite a bit of power in controlling what your starting material and final material should be in order to survive. And they do this all the time, right? Airplanes that fly, they're made of aluminum, a lot of them. Nowadays, they're being made more and more of carbon fiber, right? But the aluminum is particularly susceptible to failure like this, and so they actually monitor it after every X number of flights. They take their machine and they scan it, right? Their CT scanner, and they're checking for, or ultrasonic scanners, they're checking for flaws, right? And they're seeing how much they grow because they know how the biggest, what's the largest that thing can get. Which is pretty cool that we can monitor that as engineers and plan around it to know how many flights that plane can take before replacing that component. Anthony?
Now, what was an ultrasonic scanner though? Could that also cause some of these cracks to grow as well?
Yeah, you betcha, right? Ultrasonic scanner, that's producing a little vibration. Will that grow the crack? Sure, probably a tiny, tiny insignificant amount because the amount of energy from the ultrasonic is really, really small. Nothing compared to the flexing that the plane's experiencing when it flies. Okay, let's answer the question, how do you read and use log plots? This came up last year as well. I forgot to talk about it sooner. Log plots are useful for making things that aren't linear look linear. That's really why we use them. That's the only reason why we use them. Back in the day when we didn't have a computer that was, could solve all our problems for us easily, it was much nicer to make complex mathematical expressions look linear, and sometimes that can be done by plotting them on log plots. An example is what we saw last time. Again, you had this dA over dN equaled A, the range in the stress intensity factor raised to the n. That's an exponential figure, right? But if you plot it on a log plot, where you're plotting natural log of dA dN, plotted against the natural log of the stress intensity factor range, it looks linear, right? So how do you read these plots? First thing to know is that their major and minor axes are scaled differently. Major and minor axes, what I'm talking about is major and minor tick marks is maybe a better way to put that, right? So your major tick marks are equally spaced. They go from here, right? Here's a major tick mark, a major tick mark, a major tick mark. But the minor tick marks are not spaced equally, right? You take this big jump and it gets progressively smaller as you approach the major tick mark. Make sense? Every major tick mark, it goes up by 1 decade or 1 power of 10, right? It goes from 10 multiplied by 10 is now 100. Multiplied by 10 again is 1,000. So if we did the next one down, it would be 1, and then it'd be 0.1 below that, and you could keep on going. Because of that, your log plot can never reach 0, right? It's just going to keep on dividing by 10, and it'll never actually reach 0, okay? The other thing to note, when you look at the minor axes, let's take this one. If this is 100, then the next minor tick mark up is going to be 200. This one will be 300, 400, 500, 600, 700, 800, 900, and 1,000. But instead of going to then 1,100, the next tick mark up would be, right there, I guess, and it would be 2,000. Right, because you go 1,000 to 2,000. Same right here. This is 10. The next tick mark up is 20, 30, all the way up until you get to like 80 and 90 up here, but then it jumps to 200. So that is how you read these plots. Are there any questions I can answer on reading log-log plots? If it's been a while since you've seen them. Okay, if you do need a refresher, our TAs are great, they can give you a hand. Yeah, Arthur?
When, is that 20 or 28?
That's an ugly 20. 20. They go in powers of 10, right? Okay, let's keep going. So what other factors affect fatigue life? Mean stress. So mean stress. Let's say that your materials have the same amplitude, stress amplitude. What was stress amplitude again? Again, stress amplitude, if your stress is doing something like that, your stress amplitude is this distance divided by 2. So that distance is sigma A, right? Yeah, Rosa?
So what if 0 is in the middle? Why do we take the amplitude divided by half and not just go?
So like what if this is 0 there,
Yeah.
up to like, I don't know, 100? Because it's still the range that we're talking about, right? So it's going to be, when we look at dA dN equals A, oh, sorry, let me just rewrite that, equals A times delta K, today, delta K to the N. Delta K is equal to the K max minus the K min. So the maximum stress intensity factor subtracted from that, the minimum stress intensity factor. So it's a range, right? So in other words, it's going to be the oscillation around some point, okay? So that's your stress amplitude. That's not the same as your mean stress. Your mean stress is up here, right? That's your mean stress. So if two materials have the same stress amplitude, right? So let's say 100 cycling to 200 versus 50 cycling to 150. Both of those have a stress amplitude of 50. Wait, math. Sorry. Oh, that's right. Is that right? Yeah, that's right. They both have the same stress amplitude. They have different mean or average stress. And so if all things are equal, then the mean stress, the one that is larger, will give you a shorter fatigue life. Rich, I think you have a question on that on the homework, where it turns out the range is the same, but the average is one's higher than the other. The mean stress is higher. Yeah, Arthur?
I have a question. If we have a homework problem where there's like, for example, the first one where there's 2 types of stresses, one that's like 500 and the other that's 200.
Okay.
If we have to plug that into, if we have to plug a stress into the equation to find say KIC,
Okay.
do we plug in the amplitude or just the one that's the biggest?
Great question. Depends on which equation you're putting into. If you're using Griffith fracture toughness equation right here, this is telling you when something breaks. So that will not break from a range. That's going to break from a maximum value, right? But if you're using this equation right, where do we have it written out? Right here. If you're using this equation, that you use the range for, right? Your sigma, your delta sigma there is the change, okay? Anything else I can clarify here? Okay, other things that can influence it. Surface effects, obviously, we know surfaces are a problem because your crack is basically twice as dangerous at the surface. If it's the same length, it's twice as dangerous, right? So because of that, there's a lot of surface treatments that they do. For example, when you do machining, all you're doing is you're scratching the surface in a controlled way, right? You take your sandpaper and you're just scratching it, right? Hopefully you're removing flaws that were there that were larger than the flaws that you're going to put in there by scratching it, right? So if you have like a big millimeter deep scratch in your component, but you polish it with like a 600 grit sandpaper, your scratch marks are tiny, way smaller than 1 millimeter. So you've overall improved your sample there, right? They do other things though. They'll do something called shot peening, right, or case hardening. Both of these place the surface in compression. Again, crack growth, we're assuming that cracks don't grow under compression. That's valid in some circumstances. And so if you can put something in compression, then before it can reach a tensile state, it has to overcome that compression, right? So, right? If tension is going to make that crack grow, but you start it off by squeezing it, it has to overcome first that squeezing force, and then it can start pulling it apart. So putting it under surface compression is a great idea. One way they do that is sharp pinning, where they basically hit it with like BB guns, right? It's more scientific than that, right? But they basically spray it with little tiny beads, and it puts a bunch of little indents in each one of those dense material around it and puts it all under compression. Another way, which we'll talk about in a few chapters, is case hardening, where you diffuse in a larger atom or just atoms that will fit in between the other atoms and squeeze it closer together. So you can do it with carbon or nitrogen. That's how titanium carbide or titanium nitrides are made, that have a harder surface than the bulk underneath. We'll come back to that later. All right, let's talk about other factors. Thermal stress, right? We've mentioned this over and over, that even though you don't think your part's under oscillating stress, temperature range can be a big deal. So the stress that it produces, the thermal stress, is going to be equal to the difference in the thermal expansion of your two materials. That's delta alpha L, right? So basically you have like thermal expansion L for your, let's say, ceramic, minus the thermal expansion L for a metal. These things are typically about an order of magnitude apart. So that value right there could be an order of magnitude. So call it 10 for a moment. Or, well, I guess it depends, right? That's multiplied by the modulus of the material that's going to fail times the change in temperature. So if you have a ceramic, right, a big ceramic plate, and you bond it to a piece of metal, and then you cycle this thing, put it in ice water, put it in hot water, ice water, and hot water, the one that's going to break is definitely going to be the ceramic, because it's the one that can't tolerate stress, or strain, excuse me. Right? So you could calculate the amount of stress generated by plugging in the modulus of your ceramic multiplied by the difference in thermal expansion and the difference in temperature. That will give you your thermal stress. Questions on thermal stress? Yeah, Jeff.
So they use the modulus of the one that will break.
Modulus of the one that will break. Now, if you don't know which one's going to break, you could calculate it both ways, right? You could plug in what's the stress, assuming ceramic, and plug that in. Then you can calculate the stress in your metal. It's valid, and it's the same stress. One's going to be compressive, one's going to be tensile, but it's going to be the same magnitude. The one that's under tension is usually one that breaks, and it's usually the brittle material that breaks. Okay? Can I answer any questions about this, Rosa?
What does that example mean? What you're talking about the bridge?
Oh, okay, so we care about thermal expansion because it's actually a really big deal. If you think of roads are asphalt, which is like a type of ceramic, right? It's a brittle material. You can't bend a road without it breaking very easily. And they put additives in it to try and make it be able to, but it doesn't bend very well. So if you have a bridge, which is over air, right? So it's got air above and below it. When that thing goes day to night, or winter and summer, it's going to have a more severe temperature fluctuation than just the road, which is connected to the ground, because the ground kind of keeps it at a more homogeneous temperature. Bridges can have a much more severe change in temperature because there's air above and below them. So because of that, they can expand and contract a whole lot more than just the road. So this causes problems, and it would actually cause it to break if you didn't build in some wiggle room. So when you drive over these things on bridges, you've all seen them probably. What that is, it's wiggle room that allows the road to expand and contract. So they call them expansion joints, right? And they're a big deal. So again, in your statics class, if you ever took statics, if you've taken it yet, you notice that they'll pin one side, but they'll put the other side of the bridge on a roller. That's exactly why they do this, right? You can't pin both sides or you generate huge thermal stresses. Okay. Let's talk about creep. Creep is another property that's really important for material science. What is creep? Creep is time-dependent, permanent plastic deformation, right? Which means if I take something like this bottle, right, and I hold it here like this, it has a stress on it, right? The weight of this water and the fact that I'm supporting it from the ends tells me that there's a bending moment in this, right? And it's going to have a maximum stress in the middle of this bottle, wanting to bend this bottle. And it's not bending, right? But if I hold this thing here for a year or 2 years or 10 years, you might notice that it actually bends quite a bit. Right? It's just a really slow. So think of creep. Creep is plastic deformation that doesn't happen immediately. It takes a long time for it to happen. You can see this in bookshelves, right? In this bookshelf, it had a bunch of science on top of it, and over the years, it's groaning under the load of science, and it's creeping, right? That's absolutely why, right? Or maybe it's the Godzilla right there. I don't know. Yeah. Right? So that's creep. So creep, again, just remember, it's plastic deformation, but it's one that occurs over a time scale which is longer than your typical plastic deformation, right? Something that's happening slowly. So how do we model creep? It's important to know about. We have a model that basically shows strain over time. And you're going to have some initial elastic strain. We'll talk about elastic versus plastic later this semester. But elastic is the recoverable, reversible one. Somebody had a question about that a few classes ago. Like you take a rubber band and you stretch it, it's going to go back. So that's the elastic part. So as soon as you load something, there'll be some elastic strain. But then you have this primary, secondary, and then tertiary creep. right? So primary and tertiary are non-linear. They do things that are hard to predict. But secondary is linear. Linear things we like because we can predict them. Once you know what that rate is, you know it's going to be in 5 years from now, right? And if you're designing a home or a bridge or whatever, that might be useful things to know, right? So let's talk about this. The expression that we use to show the strain rate, so that's epsilon with a dot on top of it. The dot on top, again, just means the rate. So the rate of strain is going to be equal to K times sigma raised to the n, so that's your stress raised to some exponent, multiplied by the exponential of negative Q over RT. Q is what we call an activation energy, and we will come back to it many, many times in this semester. There's not one activation energy for materials. There's a different activation energy for whatever your process is, right? So there's an activation energy for diffusion, which describes how atoms hop around in a lattice, and there's a different activation energy for creep. And there's a different one for electrical conductivity, which is how electrons move around, right? So it's just an activation energy. And so this is what we call a thermally activated process, right? Meaning the higher the temperature, if you plug in a higher and higher number here, since this is exponential to that negative 1 over a large number, exponentials can become a larger and larger number. So the higher the temperature, the faster your creep strain rate. And maybe that makes sense. You have a bookshelf at room temperature versus one maybe in like Arizona, where it's warmer, you might expect it to creep a little bit more because it's warmer, right? Yeah, Rosa, question?
Is the exponential part exponent to the exponent n?
That's the same as writing E, like E natural number to negative Q over RT.
Oh, okay.
Yeah, that's what that is. Any questions on thermally activated properties? We will come back to many of these this semester. It affects tons of things, right? Basically, the key thing to remember, temperature plays a role, and that role is exponential, right? It's in an exponential. So as you heat something up, things become dramatically different, right? Better or worse, depending on what your property is. They become dramatically different because it's a thermally activated process. And this also means at low temperatures, you don't expect to see a very fast strain rate, right? So if you take that same bookshelf and put it in Antarctica, it's not going to creep nearly as much, right? Because the rate is slower, okay? Any questions I can answer about this? Getting confused looks from Morgan. No? Yeah.
What's happening like on the small level, basically? Why is the temperature
Creep has to do with atoms sliding past each other, basically. And for atoms to slide past one another, they need energy, right? Just like if you wanted to leave your row, you need to spend some energy to get up and wiggle past people. Atoms do the same thing. They need a little bit of energy. So if you take away all their energy by cooling it down, then they don't move as much. Yeah, Anthony?
I just have a curious question. If you were to approach the temperature, make the temperature really close to absolute zero, would it cause those atoms to just fall apart, or would it?
They would not fall apart, but there would not be motion, right? And we can't get all the way to absolute zero. We've gotten really close, but we can't get there.
Right. I was just curious though. If you got really close, would it go continue all along that curve with the gravity, or
you'll see that the strain rate will approach zero. The slope, right? The slope of this strain versus time here. This slope is your strain rate, and at lower and lower temperatures, it's just going to approach zero.
Oh, okay.
It's going to head towards. It'll just be not changing at all. So we often, again, we're going to use another log plot. This time it's slightly different. We're going to plot natural log of our strain rate against 1 over temperature. The reason we do this, imagine that you take natural log of both sides, right? So now you've got natural log of your strain rate is going to equal. Oh gosh, it's going to equal natural log of K plus, let's write this out. It's not erasing, there it goes. Plus N times natural log of sigma plus negative Q over RT, right? So the reason we do this, basically all of this is a constant, right? Which then says, if you set that to be y, then this is going to be your b plus mx, where x is then going to be 1 over temperature. Therefore, the slope of this is just negative q over r, right? Your slope right there, the slope is the activation energy. That's the thing you usually care about. That's what you're usually trying to solve for, is the activation energy. If you plot this natural log of strain rate against 1 over t, the slope of that line will be your activation energy divided by r, well, negative activation energy divided by r. Can I answer any questions about that? Yeah.
Did you say that constant is m? So we would just say what m, x, and b are again?
Oh, so y equals mx plus b is just a linear equation.
In the
So all of this constant, that's b. All of this thing, that's all b. X is 1 over t, and then q would be, m would be q over, negative q over r. Okay? Yeah, question? T is your temperature. R is the gas constant. Again, gas constant is and we'll pick up here next time and wrap this up and then start chapter 3.